Alright guys, continuing on to the third video. So what we've seen so far is that the scientific method is a powerful approach to understanding the world. In fact, so much so that one of the leaders of one of the world's major religions said, if science proves some belief of Buddhism to be wrong, then Buddhism will have to change. And that's really such a powerful statement coming from a religious figure, and it's really something that is actually pretty wise. This next picture is a really interesting look at how animals view the world, looking at an unusual behavior in a lab rat. What they found was that they had put this lab rat into this special cage that whenever the lab rat stepped on a lever in the corner, the food would come out of a little hole in the side of the cage. And so the lab rat would start to learn as he stepped on the lever on the side of the cage that he would get a pellet of food. Now, some of the lab rats actually developed really interesting ways of understanding that if they stepped on that lever they would get food. Sometimes they would do a little routine where they would move around in the cage and then step on the lever and get the food. So they actually believed that their behaviors had some kind of influence on the getting of the food. And so sometimes we as humans do similar things to this, where we see some type of behavior thinking that it leads to an outcome. Like, for example, sometimes baseball players do a certain number of taps or kicks, or they touch their hat, or they touch something else, and think that that will help them in the game, or help them hit the ball, or help them catch the ball. And so that's one of the ways that that superstitions can actually manifest themselves in not only in humans but actually in animals. The scientific method, however, is one way that we can combat superstitions. In the scientific method, we observe some type of phenomenon, something happening in the world around us, and propose an explanation for that. Then we test that explanation through a series of experiments, making sure that those experiments are accurate and valid, or we revise it and explain the thing some other way. Scientific thinking is always empirical, meaning that it's based on experience, observations, and they are rational, testable, and repeatable. So that's what a good science experiment does, is that they make sure that you can test it, repeat it, and be able to basically provide proof. So here is an example of what might be a possible test question coming up on your first test. Which statement below is based on empirical information? Knocking on wood ensures a good outcome. Number 2, since most elementary school teachers are females, females make better elementary school teachers than males. Number 3, we had a really cool spring this year, therefore climate change or global warming must not be happening. Or number 4, chicken is a healthier source of protein because it contains less saturated fat than beef. So if we're going to look at something that's empirical, something that's testable, knocking on wood, ensuring a good outcome, good is something that's hard to explain, and then knocking on wood, ensuring a good outcome is not something that we could test. Since most elementary schools are females, females make better elementary school teachers. That is not something that's actually testable. The third is funny because I always hear, well, it was really cold and so global warming didn't happen. Global warming and weather are not the same thing. Climate change is not the same thing. Climate change is actually that scientists have looked at weather patterns over the past 100 or more years, and they've been able to look at are temperatures increasing on average, and they have actually found that temperatures do increase on average. So that one's not true. So number 4 would be the answer. Chicken is a healthier source of protein because it contains less saturated fat than beef. Could we test chicken and test beef and find out if it had less saturated fat? Absolutely. We could do an experiment on the saturated fat in different protein sources. So make sure that you're understanding how to go through questions like this, and I'll try and provide some more of them as we go along. A beginner's guide. What are the steps to the scientific method? Well, one of the first things that you find that scientists often do is that they measure things. Measuring things is one of the best way to find out facts about the thing that we are observing. So the scientific method is not necessarily a rigid process to follow. It's not something that is set in stone and only goes around in a circle or only follows a linear path. It's not a cookbook or a recipe. It is more of an adaptable process. It's something that can be revised and be changed and go back and make more observations, but we're going to go through it a little bit further as we continue on in our slides. The basic methods, basic step to the scientific method is that first we make some kind of observation, we formulate a hypothesis, devise a testable prediction, conduct a critical experiment, and draw conclusions and make revisions. Now it seems like from this that the basic steps of the scientific method are set in stone, but that's not exactly true. We can always go back and move around and make different observations, check different hypotheses, make different predictions, test things in different ways using different experiments, and go forward and move back and move around. The scientific method rarely proceeds in just a straight line. Conclusions, for example, often lead to new observations and refined hypotheses. So we often change our mind based on different conclusions. What would you do when something that you believed in turns out to be wrong? Like the question about the link between vaccines and autism. If you found out that the scientific method had been followed and it was proven that there wasn't a link between vaccines and autism, then that would tell us that we should change our minds. And that's one of the great things about science, is that science actually allows for people to say, hey, maybe we've been saying that the earth has been flat for all of these years and we actually found out that it was round, so we should change our minds. That's part of the tenets of a good science experiment. Or maybe we find out that things change over time, and when we look at fossils, we see that changes in the bone structures prove that animals have changed over millions of years. So it tells us that we should be able to change our mind. It's what's called self-correcting. One of the experiments that we'll look at here is, does echinacea reduce the intensity or duration of a common cold? And so a lot of people take echinacea when they think they're starting to get sick, because they believe that taking echinacea will help them to reduce the intensity or the duration of those symptoms during a common cold. So we can test and find out whether or not taking echinacea reduces the intensity or the duration of the common cold. That is something that is testable. So the first thing that we would do, or really the second thing we would do, is formulate a hypothesis. Echinacea reduces the duration and severity of the common cold. Is that something that is testable? Absolutely. We can test that statement. So to be most helpful, a hypothesis must accomplish two things. It must clearly establish mutually exclusive alternative explanations for a phenomenon. So what that means is we have to be able to look at two ways of doing things, and it's either one or the other, mutually exclusive alternative explanations. So either taking echinacea does reduce the intensity of a cold, or it doesn't. And so it must generate some kind of testable predictions. In devising a testable prediction, we can only evaluate the validity of a hypothesis by putting it to the test. So we can look at whether our hypothesis is valid or whether it's invalid. And researchers often pose a hypothesis as a negative statement, proposing that there is no relationship between two factors, and that's called a null hypothesis. In devising a testable prediction from a hypothesis, keep in mind that there are often several possible explanations that could be true. And so, do we always know that we have proven our hypothesis? No, we've often just shown that there is a link between one hypothesis and the different explanations that we're coming up with. So in testing a type of prediction or turning it into a hypothesis, the goal is to propose a situation that will give a particular outcome if your hypothesis is true, but that will give a different outcome if your hypothesis is not true. So an example of a hypothesis would be eyewitness testimony is always accurate. So our prediction could be that individuals who have witnessed a crime will correctly identify the criminal regardless of whether multiple suspects are presented all at one time in a lineup, whether or not multiple suspects are presented one at a time or all at a time in a lineup. So if you're thinking through this, think about what you've seen on all of those crime scene type of shows where they have the criminals standing on a background that shows their height and that shows a bunch of different people, and the person who witnessed the crime is saying, it was number 3. Number 3 is the person, and I'm sure because I saw him. And one of the things that we find is that often eyewitness testimony is not always accurate. In fact, it's usually not that accurate, because whenever there's a crime scene that's going on, a lot of times the eyewitnesses are only looking at the gun, not looking at the person that has committed the crime. So if we're going to propose a hypothesis here, echinacea reduces the duration and severity of the symptoms of the common cold, we can devise a testable prediction. And that is, in one set of people, individuals treated with echinacea, and the other set of people, individuals not treated with echinacea. So we have two different groups. Some that are presented with the echinacea and some that are not.